Hey physics. So today we are going to be looking at the race of the round tulips. Anyway, check out the video that's probably directly above this one to be able to see the setup of the problem. But here I actually wanted to go ahead and discuss the theoreticals of the problem and see if we can't come up with an answer on who's going to win the race of the round tulips. Of course, we're going to turn this into a lab, and here it is with you know, kind of in a more lab-like setting. All right. So at any rate, we have the round tulips, and I got different round tulips than the ones that were in the video, but here we have basically some round tulips. We have this one, which I'm calling a hoop, and this one, which I'm calling a disc. We also are going to include the billiard balls, but the billiard balls look a lot like this old earth here, and there's a sphere. Okay, so those are the three objects that we're going to be running down these inclines and seeing how their behavior is, and seeing if we can predict their behavior. Okay, so we start off with a conservation of energy statement, that the energy initial is equal to the energy final plus any work that's done. In this case, there would be some work done by friction, but it's pretty minimal because there's no slipping of the disc, so we're just going to ignore friction. At any rate, here we go. I'm going to take a look at my work. Energy statement, energy initial equals energy final plus work. We just said that there's basically going to be no work done, so we'll get rid of that term. All right, well, great. We know that the energy initially is going to be mgh when the round tulet is going to be placed at the top of the incline like this, and then it's going to roll down the incline like that. Okay, now that's my assistant Maddie. She's going to be helping me today. All right, and so the original energy of the round tulet would be mgh. Now some of that energy gets turned into kinetic energy, 1/2 mv squared. Okay, but some of it also gets turned into rotational energy, and that's how this seems a lot like the car going down the incline, except the car didn't pick up rotational inertia, did it? This one does. Now here, what we've done is just insert the moment of inertia for a hoop, which hopefully you've looked that up by now and found that it's mr squared. And then we've also made a substitution that omega, this weird looking W, that's an omega, of course, that means angular velocity, right? But the angular velocity is equal to V final over R, okay? At any rate, so I've substituted those in, okay? And now, I was supposed to have all this organized beforehand, but that's the way of life. Okay, you notice that the mass canceled out here, and the radius squared, cancels out here. Mass, everybody had mass in it. Now this leads us to one conclusion about this, which is kind of strange. Okay, and this is only good theoretically, which is, of course, that the mass of the object doesn't matter. What? The other thing that's kind of strange about this prediction is that the radius of the object doesn't matter. We're probably going to run a test on those at the end of this old lab to see if that's true or not. But for right now, it seems as though the mass of the round tulet and the radius of the round tulet doesn't matter. Weird, but that seems like what the theory is telling us. All right, now if I go 1/2 plus 1/2, I just get 1 whole, and there it is there. And then I just divided everybody out by mass, and then I got this statement that V final is equal to the square root of GA over H. All right, and now we want to know how long it takes for the hoop to go down the hill. All right, Well, I wonder how long it would take. And we have to come up with, you guessed it, yet another equation. All right, and in order to do this one, what I said was, well, okay, how long does it take the tuit or the object to reach its final velocity? Well, we've got the distance is equal to you should recognize this at this point, which is your average velocity times your time. Now we know, of course, that we're going to start this off from 0 initial velocity, so this whole term goes to 0. Okay, so this ends up being the time is equal to 2d, 2 times the distance of the incline, times divided by the final velocity of the thing. Okay, so oddly enough, the only thing it really seems to depend upon is how high is the incline, h, and how long is the incline, d. All right, now we're going to take our time and we're going to show those measurements in just a second, and Maddie's going to help me do that. But we can go ahead and go over the theoreticals for the disc and the sphere while we're on the subject, okay? And okay, so let's go over it for the disc. Well, for the disc, you have almost an identical energy statement. Okay, energy initial, mgh, kinetic energy, 1/2 mv final squared, moment of inertia. This time, notice that the moment of inertia this one is for the disc instead. Okay, now remember, this is the disc and this is the hoop. Okay, anyway, remember, hula hoop, I don't know, disc, frisbee disc. Okay, at any rate, so this time when you put in the moment of inertia for the disc, its moment of inertia is 1/2 mr squared. Now, well, everything else cancels out just like it did for the hoop, except that our fraction's different. Instead of having 1/2 plus 1/2, we end up with 1/2 plus 1/4. Well, that makes 3/4, of course, and then when we solve it, we come up with the final velocity is actually 4/3, or the square root of 4/3 gh. Okay, now that's a little different, but at any rate, we've got that. Okay, well, we do the same thing, you guessed it, for the sphere, and I'm just going ahead and doing all of my shapes at once here with my theoretical discussion. Almost the same statement, mgh, our initial potential energy, plus our final kinetic energy, 1/2 mv final squared. But this time, I put in the moment of inertia, for a sphere. Okay, so we're going to look at the sphere this time, all right? Anyway, that's why it says for a sphere up there, haha. Okay. At any rate, so everybody knows that the moment of inertia of a sphere is 2/5 mr squared. No, you're not supposed to know that. You should be looking that up. You can find these moment of inertias in your physics textbook. I'm getting newfangled, and I actually looked them up online. Holy moly. At any rate, it's pretty easy to find these shapes online. All right. Well, at any rate, this ends up turning into this statement, and this time we have 7/10. I had 1/2 plus 2/5, and I just went ahead and found a common denominator of 10 and said 7/10 there. That gives us this weird thing, which is the square root of 10/7 gh. Holy moly. Okay, and now we can be able to find what the velocity is of all these different things. Okay, so that's how we're going to do it. And now the next thing I'm going to do is me and Madison are going to show how we're measuring, and then we're going to show a page where we're actually going to list all those measurements for you in a nice orderly way, so you should be able to make your predictions. All right, so here we'll be right back with you. Okay, so there's Madison. There's the incline plane. Okay, and Madison, how tall is that, or what's the height of that incline plane?
0.2 meters.
0.2 meters. Okay, and then actually you can see we've got meter sticks laid out on the incline plane. But Madison, how long is the incline plane, or what's the distance of the incline plane?
1.45.
1.45 meters, okay? At any rate, I think I might have used 1.5, but anyway, you guys can use 1.45 if you want to. Now, here we're going to use a different incline plane for the old for the sphere, okay? And you can see here we've got the pool balls loaded onto what I'm calling the Galilean ramp. All right, and well, what's the height of that thing, Madison?
0.1 meters.
0.1 meters, okay, 10 centimeters. How long is that incline, Maddie? She does go by Maddie, by the way.
2.5.
Okay, and it's 2.5 meters long. Okay, at any rate, so those are the inclines. That's the information that you need in order to be able to get these done. Okay, so here, as I promised you, here, will you hold that for me? Well, actually, I don't know. Oh yeah, right here. Okay, and now I'm going to go ahead and write these down for you. The height of the disc and the hoop are going down as both 0.1 meter and 0.1 meter. They both have the same height and they have the same distance down the incline, which was 1.45 meters, 1.45 meters. You should be able to use this to find the time of the hoop and the time of the disc. Okay, and then last but not least, we said that the height that the, oops, stupid Lipkin. We said those were 0.2 high, didn't we? All right. Yeah, 0.2 high, sorry. Okay, anyway, I did have the distance right. Okay, and now for the sphere, we said that one was 0.1 meter, and that one was 2.5 meters long. Now we have our stuff. You should be able to find the time that it takes for the hoop to go down the incline, and the time that it takes for the disc to go down the incline, and then the time that it takes for the sphere to go down the incline. These will all be theoretical answers, and these are all ignoring friction. All right, we'll be right back at you. Okay. Oh, let me make sure we're still good. Okay, so now we're going to get Maddie to do our math for us. Okay, there she is. Okay, Maddie, oh, look, for the first one, we said that the distance was 0.2 meters, and the distance of the incline was 1.45 meters, and the height of the incline was 0.2 meters. What'd you get for your total time that it takes?
2.1.
Okay, so for the first one, the time that it takes for the hoop is 2.1. Okay, put seconds. Thank you. Okay, and now she's going to do the one for the second one. Okay, there, look at her go. She's going to find the time it takes for the disc to go down the hill. What'd you get for the disc going down the hill?
1.8.
Okay. There she goes. And then last but not least, we said that the sphere was only going to go from a height of 10 centimeters, 0.1, and then it was going to go down a longer incline of 2.5. But how long does it take that old sphere to go down the incline, Maddie?
4.2.
Okay, so 4.2 there. Okay, and now here are our answers. We think it's going to take 2.1 seconds for the hoop, 1.8 seconds for the disc, and 4.2 seconds for the sphere. Okay, now of course you physics students will have noticed that we didn't say nothing at all about our final velocity. You should include what was the final velocity of each one of those, because you had to know the final velocity to find the time that it took, didn't you? All right, the next segment we're going to do, we're going to get one more person to help us, probably Jennifer, that you guys have already met, and she's going to help us film, and we're going to actually run the experiment, and let's find out, after all this time, who is going to win the race of the round tuits. All right, and we'll also film how long it takes for the ball to track down the incline plane, what I call the Galileo's ramp, but that's for astronomy, not for you guys. At any rate, we'll be right back with you in just a minute. Okay, so we had to get Jennifer to help us film. Anyway, Maddie's going to roll the disc down. That's not the disc, that was the hoop. She's going to roll the hoop down the incline. You know the incline has a 0.2 meters high, 20 centimeters high, and it was 1.45 meters long. We know it's supposed to take 2.1 seconds. I wonder how long it's going to take. We're about to find out. Anyway, okay, 3, 2, 1, start. I actually got 1.7 seconds for that. Anyway, I think I was a bit late. But that's what I actually got. And I'm actually, stay right there, Jen.
Again?
You know why they call it research, don't you, Maddie?
No.
Because first you search, and then you research, and then you research, and then you research. Anyway, that's my professor's joke. All right, do it again. 3, 2, wait, okay, 3, 2, 1, start. Maddie, you were early. She jumped the gun on us there. Do it again, do it again.
Okay.
I shouldn't have said research so many times, huh? All right, 3, 2, 1. Oh, holy moly, we've got problems here. You pushed it down the incline, by the way, Maddie. Just let it go. Don't push it down the incline. Okay, well, we hope last but not least. 3, 2, 1, go. 2.1 seconds is what we got that time. I felt like that was a reasonably good, like I started it. That's what we were supposed to get, wasn't it? Holy moly! Okay. Anyway, that's what we got for that one. We might as well just run it again. We're going to run the disc this time. Let's see what happens. This was supposed to go faster, all right? And it should only take, I don't remember, wasn't it 1.7 seconds or 1.8 seconds, Maddie?
1.8.
Okay, she says 1.8. All right, let's see if we get this one right. 3, 2, 1, start. Oh, Maddie, we're early. We got 1.65. Do it again, Maddie. 3, 2, 1, start. That was a good one. Oh, 1.7. I can't believe it worked out that good. We're all over it here. Okay, one more time. We're going to set up and do this one. So go ahead and hit pause. Yeah. Is the only one you got to do. Okay. So here we are again. We're going to do the sphere going down the incline. You can see that this one's a longer incline. This one was the incline was 2.5 meters, and this time the incline's not as steep. We are only 10 centimeters up in the air this time. I believe, according to theory, this was supposed to take 4.1 seconds. And of course, again, you can see I'm here. I'm the one timing it. You can always pause the video and time it for yourself. That's why I'm including these videos. But at any rate, here we go. We're going to try it. All right, are you ready, Maddie? Two ready. Okay, 3, 2, 1, start. I got 4.1 seconds on that. We're going to give you another angle. Anyway, Jennifer and Maddie thought you'd like that angle, but this is the angle I thought would be better, but what the heck do I know? Not much would be the answer there, but here it is. We're just going to do it again. Here we go. 3, 2, Maddie. 3, 2, 1, start. I got 4.4 seconds that time. All right. At any rate, so you should be comparing your theoretical answers with what you were supposed to get or what your actual experimental was. Right. Now we're going to do two that we don't have answers for you. All right. You need to do your own answers for. Okay. we're just going to run it. I'm going to actually time it for you so you can see how good your estimate was. You know we're on the same 2.5 meter track, but this time we're going to jack the track up. Okay, so here we go. Okay, this time the track is, oh yeah, that was right. The track is now 0.25 meters or 25 centimeters up in the air. I'm guessing that this is going to take less than 4.3 seconds, huh? Pretty good guess, since the other one took 4.3 seconds. All right, here we go. We're just running it again. We don't have answers for you, but you physics students should be able to make a prediction. You know you should make a prediction first and then see if your prediction comes out correct. Okay, here we go. 3, 2, 1, start. Oh, I'm going to call that 2.9 seconds because I was a little late on the timer. At any rate, we're going to do it one more time just to be like wild and crazy guys. All right. Anyway, you guys aren't old enough to remember the Steve Martin skit where we do wild and crazy guys. But anyway, that's not me. That's Steve Martin from Saturday Night Live. This time the incline is 0.45 meters tall. It's 45 centimeters tall. Same 2.5 meter long ramp. Here we go. We're going to do it one more time. See if you can predict this one. All right, there we go. 3, 2, 1, start. That one only took almost exactly 2 seconds. I wonder how well your theoretical predictions matched up with the experimental predictions. Now, I promised you guys that we would do this, and we're going to do one more thing, and we'll come back to my original ramp here, and Jennifer, of course, she had no idea that I was going to do this to her, but here I have 2 radically different balls. One is a steel ball, and one is a golf ball. The steel ball has a lot more mass, and you can see it's bigger. But according to theory, and all that physics mumbo jumbo we just went through, mass and radius didn't matter? Really? Okay, well, gee willikers, Maddie, I wonder if that's true or not. We're going to go back to this ramp. She's just going to roll it right down the incline. And I went back to the low angle on purpose because, well, we wanted it to be slow. We got the best chance of actually seeing if there's a difference if it's slow. All right, so put the 2 balls on the 2 different tracks, on any 2 different tracks. She's going to roll them down. Let's see. According to theory, they reach the bottom at the same time. I don't know if I believe that or not. All right, go, Maddie. That might be the difference between theoretical and experimental, huh? At any rate, I think it's pretty safe to say, watching that old golf ball go down the incline, that perhaps matter, or mass and radius did matter. It wasn't supposed to. I've never seen it make that big a difference. So we're going to go to the cue ball and the massive ball and do it again, just to see if it makes. These balls are close, and okay, go ahead and let's run that again. Now there you did see that the cue ball landed first, not the cue ball, but the billiard ball, but not by much. In that case, they were almost identical. And now, of course, you physics students should expect the next question, which is, well, why? How come the golf ball took a lot longer, but in this case, the mass and the radius didn't seem to matter as much here? And anyway, see if you can come up with a plausible explanation on why. I'll be the first one to tell you I don't have a plausible explanation on why. I do have an experiment that showed me they were clearly different in all cases, and so that puts a little question on our theory, but I think if you go through this experiment, I don't think you can question theory too well, because of course we were accurately predicting the time, at least pretty close on all of them. Our expectations, our theoreticals were in general met up with what our experimental results were at any rate. But you know, the question is, are you an experimental physicist or a theoretical one? Which one did you find the most aesthetically pleasing? Which one are you going to actually believe? You know, the experimental results or the theoretical ones? All right, anyway, good luck on your experiment, and we'll talk to you soon.